Hello, everyone. Welcome. Thank you for joining today's webinar. This is Amy St. Croix with the Statistics Division. Our speaker today is Dr. Willis Jensen, who is an associate in the Medical Products Division at W.L. Gore and Associates, where he provides statistical support and training to innovative engineers and scientists. Willis holds a PhD in statistics from Virginia Tech and has research interests in all aspects of industrial statistics with a focus on applications to real problems. Today, we are going to hear from Willis, who is joining us from Arizona, and he will be presenting on the statistician's role in innovation. And this was a popular talk that he gave at last year's Fall Technical Conference in San Antonio. So we're happy to be able to share that with the division today via webinar. All phones and microphones have been muted except for the presenters. So if anyone has any questions during the webinar, please use the questions interface in GoToMeeting. And I'll hold all of those questions until the end of the presentation. And at that time, Willis will have some time to answer those for us. So without any further delay, I'm going to hand things over to Willis. And Willis, thank you again for presenting with us today.
Thank you, Amy, for that introduction, and thankful for the opportunity to present this webinar. And as Amy mentioned, this is based on a talk that I did at the last Fall Technical Conference in October of last year in San Antonio. And I'm going to give a little bit of background on that and what motivated that talk and what kind of motivated the this presentation. So to start off, just to give you a little bit of my background, because that I think hopes to explain some of the reasons why I've gotten involved in this particular topic in thinking about innovation and how statisticians and statistics can help in innovation. So W.L. Gore is famous for Gore-Tex fabric, which is a very innovative product that many of you may be familiar with, or if you ever had a jacket or clothing or shoes that have that Gore-Tex material in that. It's one of the primary products, but that same material that we use for the Gore-Tex fabric is also used for a variety of other applications, including medical devices, for electronic products, for filters. We've had our products on the Mars rover that recently landed last year, so our products have gone to space, inside the human body, all over the place. Now, the company itself was founded a little more than 50 years ago with a large number of associates throughout the world, and is a well-recognized company as a place to work, a great place to work and a great place to be. So given kind of that background, the company itself has a pretty strong legacy of innovation. So our founder, the original W.L. Gore, his nickname was Bill, so Bill Gore was our founder, was actually an engineer who started doing a lot of statistics work back in the 50s at DuPont before he founded the Gore company. And at that time that he was at DuPont, he actually wrote a statistics textbook specifically geared towards chemistry, people doing work in chemistry, chemical engineers, that type of work, and how to do experiments and how to do analysis and things like that. So he had a really strong appreciation for statistics and the power of statistics, and that has carried over today. I'm part of a global statistics team that works all across the company and doing a variety of innovative work. One of our more famous discoveries or innovations was ePTFE, which is essentially what the Gore-Tex fabric is made out of. Is a polymer that was discovered by Bill Gore's son, who was Bob Gore, and that particular innovation resulted in many new products that we create. And so innovation is a big part of the company. So this conversation around statistics and innovation is something that's been kind of happening more and more over recent years within the statistics division or within the industrial statistics area. There was an invited session of the Fall Technical Conference back in 2010 that specifically talked about the role of statistics in innovation, not statisticians per se, but how statistical methods could help facilitate innovation. And as a result of that invited session, there were a couple of papers that appeared in Quality Engineering in 2012. One of them was one that I helped to edit that was based on that Fall Technical Conference invited session. And then a paper in 2012 by Box and Woodall. So George Box, that is George Box's very last paper that he wrote before he passed away. And Bill Woodall, who's well known in the quality control arena. And that paper actually won the BizGuard Award for being the paper in the Quality Engineering Journal with the greatest potential for advancing the practice of quality improvement. And Bill Woodall and I did presentations at the Spring Research Conference in Cambridge, Massachusetts in 2012. And then last year in 2013, there were some sessions around the role of statisticians in innovation by several folks from Stu Janis from 3M, Martha Gardner from General Electric, GE, and Tim Hockman from DuPont. So there's been a variety of different folks have been talking about this, and this is occurring within the broader discussion in the business world and outside of just the statistical world around innovation. Even President Obama has gotten into the act and has mentioned innovation in his State of the Union addresses over the last couple of years, and funding research and looking to be more innovative as a country. So when you start thinking about this concept of innovation and how that relates to quality and statistics, there's kind of been a wave in the past that's been going on for some time around improving quality. And you think of techniques that we're familiar with, Six Sigma, Lean Six Sigma, the basic quality tools, the voice of the process, SPC, all of these tools that many of us are familiar with to reduce variation, reduce waste, and we can think of those as kind of incremental innovations, sustaining innovation, maybe process innovations, improving the processes. And then we could think of another wave beyond that that goes in not just improving existing processes, but designing new processes or products. We want to design quality into the process. So you think of design for Six Sigma type approaches, QFD, voice of the customer, DOEs, a variety of different tools that are more product innovation or design innovations. You think of kind of the category or whatnot. And then you can almost think of maybe a third wave here that talks about redefining quality. So not so much as designing quality fit, but thinking about maybe a radical innovation or a disruptive innovation that different authors and different books have talked about. In my opinion, I don't know if there really is that third wave. And there's kind of this myth out there that innovation is just this a chance eureka moment. You get this bright idea and it changes the world and whatnot. Now, certainly that can happen, but those types of innovations are relatively rare. And most of the innovations that we see around us, new technologies and things like that, are really the result of steady gains over time, building off of past knowledge, sequential experimentation. Even something like an iPhone or an iPad, which many people would say is a very innovative product, is the result of sequential gains over a long period of time that has led to kind of that product that we know today. So a lot of those tools that have worked in the past to improve quality and design quality, I believe, are still going to be very relevant in creating new innovations for the future. And there's not really this magic bullet that say, well, if I just do this, then I'm going to be able to create that innovation. It's a lot of those same tools that many of us are familiar with and have used to generate those innovations. So what I'd really like to, with that as a backdrop, what I'd like to answer or talk about today are two specific questions. So first off, I want to talk a little bit about statistical methods and how they can aid in innovation. And then the second piece of this is talking specifically around statisticians and how statisticians can play a role in innovation. Now, there's a related question to that second one. Sometimes people will say, well, how can I become more innovative? So as an individual, what can I do to be more creative and generate ideas and things like that? That one's a little more difficult to answer. But hopefully, as we talk about some of these roles and things that a statistician can do, that can help answer that related question of how does one become more innovative. So let's start with that first question. How do statistical methods aid in innovation? I really see two different ways that this can happen. So one way is the confirmatory role. So when you think of using data, experiments, tools to check the validity of existing ideas. So you have an idea, say, I think if we change this, then this result will happen. The hypothesis that we want to check. Statistical analysis and design of experiments are really good tools in a confirmatory role to confirm a hypothesis, to test the hypothesis, to determine if a particular factor has an effect on a response, or to determine if a set of factors have a combined effect on a response. So I don't want to spend too much time talking about that role, because I think that role is relatively understood. Many statistics textbooks will talk about hypothesis testing and how to confirm hypotheses and different analysis tools and statistical methods to do that. The second way that I would like to spend a little more time on is a generating role. In other words, using data to create new ideas. So this is not testing existing hypotheses or building models per se, but it's more of a focus on graphical tools, exploratory data analysis, and using those tools and graphs to generate new ideas, to come up with new solutions to problems, to answering questions or creating new questions, if you will. One way that I like to think of those two roles, on the left-hand side, that confirmatory role, the Box and Woodall paper that I mentioned earlier in quality engineering talks about the inductive-deductive concept, and that's a fairly familiar concept to statisticians, where the data leads to results. And so you think of some of those synonyms: testing, focusing, conclusions, convergence, funneling, taking the data and from that data driving to a particular conclusion. Okay, so there's this kind of narrowing or winnowing that's happening there. The generating role is more divergent. So you're taking the data, and instead of focusing in on a result, you're opening things up to ideas. So it's more exploratory, it's more questions, creation of new ideas rather than concluding or making conclusions. In Box and Woodall, in their paper, they talked about what they call lateral thinking, with the concept that they discuss in more detail there, the idea of using the data to generate new ideas. So what I'd like to do is give some specific examples from my own experience of this generating role and talk about some of those statistical methods that were used to do that. And in all of these, I have modified the details to preserve some confidentiality, but hopefully there's enough information here that you kind of understand the point here of this generating role. So the first example that I'll give has some data here. So a scientist that I was working with had some questions around the appropriate transformation for some data. So they had some historical data there, and you see the histogram of that data, some summary statistics for that, the mean, standard deviation, the quantiles, and whatnot. And they had gathered this data to use as a justification for making a change to the process. So it was a confirmatory type rule, and say, hey, here's the data, is this process change acceptable? And the analysis involved some distributions and calculations of intervals that require the normality assumption. And so the scientists who had been trained in basic statistical methods said, well, I don't really have normally distributed data. I've got this skew, right skew distribution. I mentioned these outliers up in that 6, 7, 8, 9 area. So I don't think normality assumption is appropriate, so I want to do the transformation. So in the course of the conversation with the scientist, I began to ask a variety of questions, and in that questioning, found out that the data had been pooled across multiple lots. So this was kind of a batch processing, lots processing situation, and so there were a bunch of lots. So I asked the question, well, are all of these lots similar? Are they the same? Are they different? And so we created a graph of that data broken out by lot. And you'll see in this particular case there were 22 lots. Each one had anywhere from 3 to probably 6 to 8 points per lot. And you'll see the lots number 8, 11, 12, and 20 are the ones that all have those higher values, those outlying values from that histogram. And so then the question is, well, what is different about those lots? So we looked at a variety of different factors to understand what might be different about those. And it turned out that one of the factors that we found was the test operator. So this is the operator that actually did the testing of the samples, or actually gathered that data. And you'll see that the blue lots correspond to operator C, and those are lots 8, 11, and 12 are all the same operator, and then lot 20 was operator B, and that was the only lot that operator B did. So as a result of this, now there's a hypothesis that is generated from this that says what's going on between those different operators. And in the course of that investigation, we learned that the operators were doing the tests differently, and so an innovation resulted we made a process change. We were able to remove that tail, if you will, from that distribution, eliminate those outlying values, and now have a much more consistent process. So there was no need to do a transformation. The second example that I'll give of this generating role was a situation with an engineer who had a process, and this is the yields of the process were not acceptable because of the large variability in the data. And initially, the engineer, in looking at the data, had reported some summary statistics without a graph. And you can imagine if you do the summary statistics for this particular histogram that I'm showing you here that has that bimodal distribution, they had a sampling plan in place that they were using to ensure that the outgoing product quality was acceptable, and they wanted to adjust that sampling plan based on this bimodal distribution. And when I was talking with this engineer, and the team said, no, we need to investigate what's going on. Why is there that bimodal distribution? And the response was, well, we've already been looking. We tried this, we tried this, we tried this, and we haven't figured out what is causing that difference in there. And my response to that was, keep looking. Don't try to make an adjustment or adjust that sampling plan or adjust your analysis to fit the data. Figure out what's going on in the data. The data are telling you something. And so, a long story short, there was a significant amount of effort to discover finally that there were two different failure modes that were happening as part of this testing. And one of the failure modes led to one portion of that bimodal distribution. The other failure mode led to the other portion of that bimodal distribution. And there was a series of experiments and DOEs that were done and determined the root causes for those failure modes. And as a result, they were able to eliminate that failure mode. The lower failure mode eliminated the bimodality and increased the capability quite dramatically in this. And as a result, we're able to reduce the amount of sampling needed, increase the yields of the product. And so really the point here is that the data is telling us something, so listen to that data and do something about it, as opposed to trying to manipulate the analysis or to match the data. The third example that I'll give was a situation where an engineer wanted to change a material in a process to a better one, so a raw material that was going in this process. And there's testing equipment for this material. You'll see in the current material has responses around 500, and you see kind of the box plot associated with that. But when they went to the new material, now the equipment is no longer, the equipment is only able to get response values up to 1,000. So you cannot get values beyond that. And so essentially what you have here is all of the data are censored. In that, in reality, if our equipment was capable of it, the true response would be higher than 1,000, but we don't know how much higher than 1,000 that new material is. In this case, there is a lower specification, so higher is better. So, well, it looks like that new material is better because all of the values are at 1,000, everything is censored, whereas the current material, nothing was ever censored. So in that discussion, now that we don't really have this continuous data with the new material, we said, well, we need to do some sample size justification to determine how many samples to take and whatnot to ensure that the process is capable. I mean, it is a destructive test, and so, but we don't have as much information now on that new material because of the censoring, and they didn't want to go down the path of getting new equipment. That was also really costly to get new equipment that maybe have the capability to go outside them. So they said, well, we're going to do some sample size justifications to demonstrate the capability of this process based on binomial data. And so we started, again, that confirmatory rules. We started talking about that, and it turns out that we said, well, we only do this testing every time we make a change to the process. So if they make other process improvements, they would use this test to ensure that the process improvements don't have a negative impact on this particular response. So I asked the question, well, as part of this testing, do you do other tests? And the response to that was, well, yes, we do other tests. And so my question was, well, are there relationships between this particular test and the other test? The answer to that was yes. So why don't you eliminate the test if it's redundant? The answer, long story short to that, is that there were a series of tests that were all done as part of a change, and because of that correlation between this particular test and the others, instead of having to do all of that testing, we could eliminate the test and not even need to do it anymore, which is a huge savings in cost, testing time, time to make future changes. It's part of an example of that incremental or sustaining process innovation that I mentioned earlier. So what's common in all of these examples? I think some of the general principles here is don't take the data at face value. The data contains information that leads to innovation, but you have to dig deeper. You have to ask, why are the data this way? What's the explanation for that bimodal distribution or that skew distribution, that censored data? Understand why. The data departures are a good thing. So we like to see outliers. We like to see skewness because they tell us something different about the data. So I'm not a huge fan, personally, of robust statistical methods that minimize the impact of those departures. As a result, if you want to be able to have innovation, you need to accentuate the outliers as opposed to hide the outliers. Look at those departures, figure out what's different, because that's where the information is extremely valuable. Graphical tools are essential. So one of the software that we use is the JUMP statistical software, which has Graph Builder tool, which is a very nice dynamic tool that allows you to look at a lot of different graphs, a lot of different processes, lots of factors, lots of responses, and being able to explore and see what may be going on in the data that you have. And then lastly, some of you may be familiar with the real estate mantra of location, location, location. And in this case, I'm kind of copying off of that and saying questions, questions, questions. And that you always have to be asking questions, and continuing to ask questions and checking assumptions and challenging assumptions and making sure that you really understand what's going on. And it's that questioning attitude that helps to lead to that additional information, which leads to potential other innovations. So that's kind of the first portion that I wanted to talk through, is just statistical methods in general, not exploratory generated goals. Now I'd like to shift gears and moving away from statistical methods and talk about the role of a statistician and what can statisticians do and how can they help and what role can they play in innovation. So I've got here kind of 6 roles that I would like to talk through. I'm going to talk through each of these in turn. And there may be others as part of these, but these are 6 that I have found in my own experience that have helped generate more innovation. So the first one is providing a holistic view. There's a famous quote attributed to John Tukey, a famous statistician from the New York Times, and this was at the time that he passed away. He talked about the best thing about being a statistician is that you get to play in everyone's backyard. And I found this to be true. One of the things I love about being a statistician is I get to go all over the place, look with a variety of products and projects in a variety of different areas, and that variety makes every day interesting, every day a little bit different. Now, that variety in and of itself makes it easy to come to work each day, but in addition to that, that variety allows you to be able to take a step back and say, you know what, yeah, I've seen these things in all of these different backyards. How do all of those backyards connect together to form a neighborhood or a city? And for the people that we work with who are kind of very focused in a particular backyard, they may not have that holistic view and be able to see the entire neighborhood or the city in a way that a statistician can, who moves across a variety of different projects in a variety of different areas. And we need to take advantage of that opportunity we have to see that holistic view. And one of the important things in the statistics division, the statistical thinking, has been a big part of the history of the statistics division, and the systems view is another way to think of that holistic view. So that very first portion of the definition of statistical thinking, all work occurs in a system of interconnected processes, is very true. And those interconnected processes span the entire company or the organizations that we work for. And we, as experts in statistical thinking and knowledgeable in statistical thinking and understanding that there are systems and all of these processes are interconnected and relate to each other, allows us to see things that others wouldn't see. So to give you an example of what I mean by this, so I had a situation I was working with where there was a current test that was done, on finished product to ensure product quality. So the engineer had a component that was assembled into the final product, and there was some testing that was done on that component, and they said, you know what, that we can do that test after assembly, or we can do it further upstream. He said, well, we would like to be able to do it further upstream and possible, test the component, make sure the component is good before we assemble it. And recognizing that if we were to do the test after we assemble it, we get about the same result. And that saves time, that saves cost, and it's a lot easier to test the component than to test the finished product. So then I asked the question as part of this, well, can you go even further upstream? And the answer to that is, well, I'm not sure. And I said, well, where does the component come from? And I said, well, the component comes from the warehouse, and it's shipped over to our process and in that process. He said, well, why don't we test it at the warehouse? And I said, well, they do it differently than the way we want to do it. And so, in other words, what was happening is the warehouse was doing a test, shipping it to the building where the production was happening, and then they were doing a test there before they were assembling it. And said, well, why do they do it differently, or is that a problem? He said, well, it is a problem because it doesn't match the way the product is used. So the warehouse test doesn't mimic the way the product is used, and we don't necessarily believe in the results that come from that test. So then my maybe somewhat obvious question was, well, why not have them test the way that you want to? The answer to that is, well, they won't want to change the procedure. If they had a procedure in place, this was the way they've been doing it, we've always been doing it this way, is my response was, just go talk to them and tell them the whole picture. Hey, this is what's happening in this entire view. The warehouse is doing this. Downstream, this later step in the process is doing that. They're not necessarily communicating with each other or knowing what's going on in each other's backyards. And to make a long story short, and part of this conversation is the warehouse changed the procedure, changed the way they did their test, and to match what the downstream process required. The redundant testing was eliminated, a variety of time and money was saved. And this type of innovation would not be possible without that holistic view or systems view of the entire process. The second role that I'll talk about is bringing an independent perspective. So as statisticians, we're not necessarily team members on a whole bunch of different projects. We're not engineers. We're not the problem solvers. So we can approach a problem with no preconceived notions. I mean, we're not the experts on a particular process or a particular technology. And so we can ask simple questions that challenge the assumptions. We can focus on the best solutions. You're not necessarily going to be biased around a pet solution that a particular team member may have. And I think it's important to bring in that independent perspective. So to give you an example of where that's been beneficial, so I had a situation working with a team on some data analysis, and they had several lots of material, and they were wanting to look at pooling the data across the lots for a particular analysis. And in the course of that discussion, we talked about how the lot size is fixed to a specific number, say 50 for our purposes. So then I asked the question, well, how do you determine that lot size, or how are those lots defined? And they said, well, whenever we get up to 50 samples, we call that lot 1. If we do another 50 samples, we call that lot 2, etc. And I said, well, why do we use 50? Just kind of questioning the basic assumption. And he said, well, actually, I don't know where that 50 comes from. And the long story short, that the number was an arbitrary number. The lot sizes were not really based on a rational subgroup. And so it made sense to change that lot size to match more of a rational subgroup rather than some arbitrary number. And as a result of this, they were able to make their analysis easier, the data processing easier, able to reduce the amount of paperwork, and not doing small lot sizes. You're able to do larger lot sizes and whatnot. The third role that I'll mention is promoting statistical tools in R&D efforts. So R&D meaning research and development, designing new products and whatnot. So there's a lot of traditional statistical methods, such as design of experiments, which are great, and designing new products, developing new products. But it also includes some of these non-traditional tools to capture the voice of the customer. Think of surveys, think of marketing research, conjoint studies, another word for those is discrete choice experiments. And so as statisticians, one of the things that we need to do is also become experts in some of these other non-traditional tools. And I found a lot of success in working with marketing folks and business folks in using the same concepts behind good experimental planning applies to market research studies and setting up experiments for how to getting a better understanding of the voice of the customer. And the earlier in the development effort, the better it will be. The more upstream that those statistical methods can be used, the better off it will be. So an example that I'll kind of elaborate on, I had a researcher, early technology development, looking at just raw material properties from some prototypes. This person had gone through some basic DOE statistics training. They were really struggling with a particular experiment. And in this particular experiment, I found that there were a lot of factor constraints that you couldn't change all of the factors completely independent of each other. Now, this experiment was not a mixture experiment in the sense of combining percentages of ingredients together into a batch and making a solution, but the constraints were such that it could be treated as a mixture experiment. And as a result, in setting up this mixture experiment, we were able to huge gains in understanding of the materials and understanding of the technology which made things much more efficient downstream for the new product development. And one of the comments here was, this was traditionally around this early upstream technology development where you get this kind of stereotype of the mad scientist in a lab playing around with things and investigating and exploring and trying new things. But statistics is beneficial even in that situation. And with this particular researcher, he says, her comment to me afterwards, after going through a variety of these experiments, was, I'm so glad we're doing these experiments to understand the new technology. The idea here is we're going to go slow upstream and really understand the materials, understand their interactions with each other, understand the knobs and handles associated with that technology, so that when we get into the new product development downstream phases, that we can go faster. We have a better idea of how to set up those materials. So we have to challenge the assumptions, or challenge that stereotype that mad scientist or somebody that's in a lab and playing with very innovative products, that they can't benefit from statistics, because nothing can be further from the truth. The fourth role is facilitating problem definition. So oftentimes the hardest part of an innovation is really defining the problem that needs to be solved and understanding the questions that are trying to be answered. And so one of the things that I have found in my role is that I can be a facilitator. I'm working with individuals and teams because I bring in that independent perspective that I mentioned earlier. I can lead discussions and lead some of those team meetings and helping those groups or those individuals really understand what it is they're trying to answer, and forcing them to spend more time and get more specific around the specific problem. Oftentimes when you get a group together, they talk in high-level terms or general terms, and everybody thinks they're talking about the same thing, but when you get down into the details, you recognize that different people interpret different words in different ways, or they have different assumptions that they are making, and we have to uncover those assumptions so that you can get people on the same page and they really truly are on the same page. And just getting those teams together on the same page in terms of the problem is a huge benefit. So when you think about that scientific method, always starting with the question, don't let teams take shortcuts. Sometimes I'll have individuals or teams who say, well, I know what the answer to the problem is. I know what the solution is. I'm going to do this. Just jump to a solution. And sometimes that backfires on them if it's not really the right solution, or they don't have support from a team or a group to move forward with that solution. So you have to get everybody on the same page in terms of the problems, which leads to huge benefits. The fifth role is being a teacher of statistical methods. So rather than trying to be inventors or innovators ourselves, try to take the role of enabling others to come up with innovation. Helping, empowering individuals with basic statistical tools. And there's another quote from Tukey that I really like when he talks about an approximate answer to the right question and an exact answer to the wrong question. And approximate answers are okay. They get people doing the right thing. They get the right conclusions, right? So my emphasis has always been graphical tools, less emphasis on hypothesis testing, descriptive statistics. Hypothesis testing, descriptive statistics have their place, but in terms of innovation, the more important tool is around graphical tools and looking at a lot of those graphical tools and helping those individuals, those engineers, scientists, people that we're working with, helping them to ask questions about their own data. And then lastly, really focusing on robust tools. And these are robust to the assumptions that you make around the data, but what I'm speaking more of here is robustness to misuse. So if I think of a statistical method that is robust, say even if the individual puts the wrong term in the model or puts the data in not quite the right way? Are they still going to get a reasonable answer? So one example that I know of is that some of you may be aware of, that I think relates to this, is a split plot experiment, that there are certain types of experiments where if you do the split plot design in a certain way, that you get the same output whether or not the individual recognizes that there is a split plot structure. So teach them to use some of these more robust tools, methods that are going to work across a variety of situations. And then the last one that I will mention is being a cross-pollinator of ideas. So there's a book out there called The Medici Effect that is, I highly recommend it. It's a great book. It talks about this cross-pollination. The innovation is not just creation of new ideas, and much of the innovation is actually intersection of ideas from different areas. And because we play in all of these backyards, because we see a lot of different areas, we can bring people from different areas together that would create more innovation. Because we kind of stand at those intersections of ideas, we have that broad perspective. We can help cross-pollinate those ideas. And this is a question that I get asked often. They say, well, do you know someone who's doing X? And because of my broad interactions across a variety of teams, I'm able to point people to other individuals or teams and facilitate that cross-pollination of ideas. And as kind of a side note, when you think of statistical approaches or things that are new statistical methods that are proposed, many of them are simply combinations of previous ideas. Very rarely are these new statistical methods that are being proposed completely brand new. Often they're combining new ideas. So with all of these roles, we start to think about the different skills that are necessary for these roles. I think it's important to focus on not just the answers that you give, but it's the questions you ask. So you think about the types of skills that you need to be able to ask questions, being able to facilitate discussions, and those communication skills become extremely important. The skills of being able to dig deeper and probe and understand what may be really going on. The other thing that I try to do is to sell myself out of a job, in a sense. I don't want to hoard statistics. I want to give those analysis tools to as many people as possible so that I can focus on more broader, important issues. And this is something that has been discussed in statistical engineering literature, where statistical engineers are moving away from a statistical analyst type role. So let the engineers be analysts, let the scientists be analysts, let them analyze the data, give them that ability to do that so that we can be leaders of statistical engineering type projects. So our value really comes from making others more effective, in developing mini-statisticians, developing para-statisticians. Mini-statisticians is an inside joke that we have here at Gore. I personally am 6'5", so I'm a fairly tall individual, and so I'm a statistician inside joke about the mini-statistician, that most everyone that I work with is shorter than I am, and therefore they are mini-statisticians. Hahn, in a nice paper back in 2002, talked about the proactive statistician, Deming and the proactive statistician. I'll give you the citation for the paper here in a little bit, but that's an important role. A lot of the concepts that Hahn talked about are relevant to facilitating innovation. We have to have a better understanding of other fields. So we've got to increase our knowledge to finance, marketing, IT, quality assurance, the business, be able to speak the language of these other fields so that we can move across those different fields and have those interactions across a variety of different areas. And then lastly, there's a lot of talk around this big data and how that can result in innovations, how that results in new things that we haven't been done before. And I agree there's a lot of potential in big data situations, but in and of itself, big data is not sufficient. And as statisticians, we have to focus more on big impact and think about, for whatever situation we're working with, whatever the data are, no matter how much data there is, focus on the impact of the data and focus on driving impact and making contributions and adding value to our organization. And if we focus on the big impact, we'll be doing the right things, whether that data set is small or whether it's large. So the last thing I'll mention here, these are some of the references of recommended reading that I would suggest if you're interested in learning more about this topic of innovation. And so these are some of these books and papers I have already referred to. A couple of them I have not mentioned in the presentation, but these are ones that I have read that I have found to be very valuable. So that is all of the content that I have. So I turn it back over to you, Amy, or any questions?
Yes. Yes. Thank you so much, Willis. That was very informative. So it looks like we do have just a couple of questions. We got a few minutes here, so we'll try to get to all of them. Let's see. The first question that somebody asked is, are there any free graphical tools that you can suggest?
Are there any graphical tools that I find to be valuable?
Any free graphical tools that you can suggest?
So in terms of the graphical tools, I find myself using a lot of the basic ones, histograms and box plots and control charts, time series plots, scatter plots, multivariate charts, being able to, and that's where, so it's not so much having new graphical tools, it's using those existing graphical tools, but where something like a JUMP or some of the software packages that are valuable is being able to look at a lot of graphs at once and being able to cycle through those graphs very quickly because you often have a lot of different factors or a lot of things to look at. And so it's not so much new graphical tools as much as having the ability to be able to look through a lot of graphs quickly. I don't know if that answers the question, Amy, or that.
Okay, thank you. Yeah, I think they're just asking the exact question that you just answered. Let's see what else we have here. Somebody else is asking, how do you break the tendency of so many people to do one experiment and then plan the next experiment based on the results of the first, instead of just designing a new set of experiments?
So you're talking about a sequential experiment where
I believe, yes.
They don't use the previous experiment?
Correct. I believe that's what the person is asking. So they're asking, how would you break that tendency of people to, I guess, build off of the results of previous experiments rather than just developing one from scratch?
Well, so one of the things that I have found that I have found personally that I do less sequential experimentation in the sense of, so let me back up. So one famous example from the statistical literature is to use like a screening experiment, a fractional factorial experiment, and then after you drop out the unimportant factors, you project those factors and add some additional runs on top of the original experiment to do like an RSM type experiment. I have found that type of sequential experimentation where I'm supplementing an original experiment with additional data and combining it together, I have found that to be less useful just in my particular industry, and partly because it's difficult to, it's a lot easier to do one bigger experiment than a bunch of smaller experiments. And so typically the sequential piece of it doesn't come from those smaller experiments. The sequential piece comes from, hey, I've done this experiment with these 5 factors. Now I'm going to do a line extension of the existing process, or a similar product as what I've been doing before. Can I use that previous experiment to help me get a good starting place for that line extension or for that other project? So then kind of going back to the question of, you know, how do you encourage more of that, or how do you encourage more of that learning from experiment to experiment? I think one of the things that helps, clearly documentation is important. If you're not documenting the results of the previous experiments, that becomes really hard to do. So having a system in place where you can document the results of earlier experiments and making it easily accessible, not just documenting it, but making it easier to access, so that people, you know, if it's a database or where those results are stored, or a library or whatnot, then it becomes easier for people to use that previous knowledge. And if there's not that, then other than just encouraging and trying to emphasizing the importance, giving examples of where it has helped, where it has been successful, you know, some of those principles related to just driving any sort of change in behavior or practice would be valuable.
Okay, thank you for that answer. It looks like we just have a couple more minutes here. I'll ask one more question and we'll wrap things up. If anyone does need to drop off, though, I just want to let everybody know that a recording of the webinar will be made available on the division's YouTube channel, and that can be found at youtube.com/ASQ Stats Division. So youtube.com/ASQ Stats Division. So please be sure to share it with colleagues, coworkers, or anyone you think might have an interest in the topic. Okay, Willis, would you mind answering just one more question for us?
You're welcome.
Okay. So somebody.
For listening.
Yes, we've got quite a few people still on the line. So see, somebody has asked here, how do you balance innovation and compliance? For example, usually in a company there are set ways of doing things, but these ways may not necessarily be the best and most innovative.
Yeah, and that's an important question. That I do work in a regulatory environment where compliance is important. We talk about medical devices. There's a quality system and regulatory requirements that we have to follow. I think one of the important things that we found as part of that is that there are things that you have to do for compliance. And so I'm trying to think of a good example off the top of my head, but you may have to say, I'm going to establish that I have control of the process, and I have to do these certain things to make sure my process is in control so that the products that are coming out of that process meet their specifications meet requirements, they're going to be safe to use, and all of that. That I really try to focus those innovation efforts not on that data, that's the confirmatory piece, but it's more in that upstream development piece. But it is important to recognize that there is a difference there. And when you talk about purposes, oftentimes people will come with questions and they're asking compliance questions. And if there are compliance-related questions, well, how much data do I need to demonstrate compliance? That's a very different issue than, hey, I've got a problem to solve. Our yields are bad. We need to improve yields. And distinguishing between those two different scenarios are different tools for those situations. That compliance is much more that confirmatory role than the generating role that I kind of alluded to earlier. So I think just being aware of those differences is important. And when people come and you're working with individuals, recognizing that there is a difference there and using the appropriate tools for the appropriate situation.
Okay, thank you so much for that answer. All right, well, excellent. It looks like that's all the time that we have for today. If there are any more comments or questions, maybe some attendees can contact Willis via email for some further discussion. Okay, excellent, excellent. So Willis, thank you again for presenting with us today, and I hope everyone on the phone enjoyed the presentation. We'll certainly have more webinars soon, and we will announce them on our LinkedIn page as well as our website and our email newsletter. So thanks again to Willis, and I hope everyone has a great weekend.
Mm-hmm.
Thank you.